Good morning, everybody. Welcome once again to my channel. This week, we're going to be talking about PostgreSQL. And in presenting this, I am using Postgres as representative of relational databases in general. So in this video, we're going to be exploring some of the functionalities and features of relational databases as opposed to Postgres in particular, though we will explore some of Postgres's features to a degree. And note that obviously, the indexing and so on are going to be the particular solutions that Postgres has built into it, and that's not necessarily going to be universal. But seeing as how it is perhaps the most popular database, especially in this genre in use today, or at least open source wise, I think it is a good place to start. For those of you who don't know me, my name is Howie Reith. I'm a software developer who's enthusiastic about becoming as excellent a developer as he can, as quickly as he can. And one of the ways I'm looking to do that is by sharing what I've learned with other people. If you would like to reach out to me, my email address is howard.reith@gmail.com, and you can of course always feel free to comment on this video with any questions that you have. So for a brief overview, I'm going to share with you how to download and install Postgres on your system. I'm going to talk about create, read, update, and delete operations. Then we're going to go over one of the most appealing features of relational databases, which is the join functions. We're then going to discuss how Postgres does indexing. We'll then talk about aggregate functions, and finally we will talk about transactions, what they are, how Postgres does them, and what their effects are on your processes. So first let's go over installation. To install Postgres, I recommend going to postgres.org/download, and there will be directions for whatever operating system you may be running. For this presentation, I will be using Ubuntu version 20.04 running on Windows subsystem for Linux. When I am starting things up, I run the following commands that you see on the screen right there. What you need to run may be slightly different, and the instructions should help you out with that on your particular system. Though note that, like anything in software development, this can sometimes be a little bit finicky. It might take you a little bit of time to get everything functioning. But once you are on a state, like I have right here, where it says Postgres, and you have the pound or hashtag symbol right there and your cursor, everything will be ready to go, and you will be ready to code. I want to note that for this presentation, I encourage you to code alongside me. And while you certainly can grab the PowerPoint off of my GitHub and copy and paste all of the commands, I am actually going to encourage you to physically type out all of the commands that you're going to see on the screen here, because that is going to help with your own memory retention of what these commands are, how they work, and so on. So of course, you can take this course however you would like, but that is what I recommend to maximize the benefit to you. So once you are good to go, feel free to move on from this spot in the video, and we'll get started. So for a brief overview of Postgres, sort of in reference to what I talked about in my previous video about choosing a database for your web application, Postgres is a relational database management system, relational referring to relational algebra on which it is based. It's based on set theory with two-dimensional tables. You can sort of think of them as Excel spreadsheets or whatever other tool for spreadsheets you prefer. In terms of CAP, it prioritizes consistency and supports ACID transactions. It is the oldest, most trusted, most widely used database today, and it has an immense number of features and a massive open source community. For this video, we're going to be building an event planning, or the database for an event planning application. This isn't necessarily the tool I would personally choose for such an app, but it is a fairly easy one to understand and visualize, and it is well suited for the sorts of functions we're going to be exploring today. Let's get started with our CRUD operations. These are our creates, reads, updates, and deletes into the database. So the first thing we need to do is we need to create a table. And for our purposes in this, we're going to be creating a table for the states in which our events will be happening. We're assuming the United States here. So I am first going to just demonstrate for you. I'm going to copy this SQL code right here, paste it into my terminal, and boom. You can see Postgres has created the table inside of my database. So let's go over the components of this query. So first right here we have states. States is the name of the table. You can think of your spreadsheet, and states is going to be the entire spreadsheet. Every time we are referencing this table, we are going to be using its name, states, in order to reference it. State abbreviation and state name are the column headings. So you can think of two columns being created in this spreadsheet. The first one has a heading of state aber, and the second one has a column heading of state name. Now next you're going to see these things right here, char2 and text. So this stands for character, and text is just text. And then there's another one called varchar, which is those are the three most common types that you're going to see in a Postgres database. Essentially what it is text is variable length string. Like all three of these are different variations on strings. Varchar is also a variable length string, but you can insert a default fixed length into it. And char is fixed length. And let me just describe to you. So basically, let's say we had char 10, right? But let's say we had a word like duck inside of it. What it would have is it would have the first 4 characters of duck, and then it would have 6 blank characters after that. So every single one of these strings would have a fixed length of 10 characters, regardless of how much information is actually inside of them. As opposed to a text or a variable length string is going to only have as many bytes allotted to it as are necessary to contain all of the necessary data. And what this is it's a trade-off. It is a trade-off between speed of accessing this data and how much space you need to store it. Obviously, if you need to be storing all of this padding for a fixed length string, that is going to take up more space. However, since all of these strings are fixed length, you can be confident in the indexes of each item because all of them are going to be stored next to one another in memory. Thus, you can say, I want this string that is at index 50, and you can go directly to it because you know exactly where that is because every single one of these strings is exactly the same length. So the computer knows exactly where it needs to go in order to get that data, as opposed to if it were variable length, it would need to run some additional functions to figure out, okay, this is actually the location of where it is or something like that, or it would need to have a pointer system or something along those lines. Thus, if you know you're going to have some fixed length values, for example, we know all of our state abbreviations are always going to be 2 characters long. It is in our best interest to organize it as a fixed length character, a fixed length string, because that is going to increase the speed of our reads. On the other hand, if we know that it is going to always be varying and we don't necessarily care that much about speed, we can make it a text or varchar. On the other hand, if we are going to be doing a whole lot of reads, say, I don't know, if we're doing addresses for houses or something like that, you might want to have a very long, but nevertheless fixed length string. So you, as an engineer, need to make these sorts of evaluations. So primary key and unique are constraints on these rows. So primary key is going to automatically assign what's called a clustered index of that column, and we're going to discuss what a clustered index is in the indexes section. And the unique constraint is going to make sure that a state name is always unique. You can never have duplicates inside of this table with the same state name. And if you ever try to put in a duplicate entry, it is going to error out. So let's go ahead and add some data to our states table. So we're going to take this insert, and we are going to stick in a whole bunch of states in the United States. As you can see, we have successfully inserted 7 states into our table. Now let's make sure our constraints are working. Let's see what happens if we try to insert a duplicate ny value. So since it violates the unique constraint on the ny, the primary key, it's not going to let us do that. You can only have one primary key of a kind. It is the same thing as a unique constraint because of the requirements on primary keys, which we will get to in a little bit. Now we're going to have 2 versions of New York in here. And once again, this violates the unique constraint on the state's name key. And then lastly, We are going to try this one right here. We're going to have New York, and we're going to have 3 digits for our primary key. And once again, that is too long for a car to type. So just to make sure that everything got inserted into our database correctly, let's go ahead and take a look at them. So we do select star from states. This is pretty much as classic as SQL can possibly be. So this returns to us this little table right here. We can see our state abbreviation and everything that we are looking to have right here. Now, oh no, we've been told that Canada is in fact not a state in the United States. Well, I guess we're going to have to delete it. So we are going to run our very first delete statement. So delete from states, where state abbreviation equals CN. Now obviously you could do the exact same thing with state name. It just so happens that I wanted to do it by the primary key right here. Let's go ahead and create another table. These are going to be the cities inside of our states that our events are taking place in. So I come over here, and boom, I have successfully created another table. So once again, let's go over this. You're familiar with a lot of this, but we have imposed some new constraints here. So not null requires that a text simply not be null. So this name field right here is essentially required inside of this table. This symbol right here, the triangles pointing in opposite directions, means not equal. So we're setting up a variable character 9 here, so it can grow or shrink according to however many digits they have in their zip code. But we will not accept an empty string, so it cannot be blank. Hypothetically, this does not constrain it against having a 1-digit zip code, but it at least prevents the user from creating a city that does not have any zip code whatsoever. References constrains a value to be present as a primary key in another table, in this case a states table. So when we are putting in our state abbreviation, if the state abbreviation that is put in is not in the states table, if it is, say, some hypothetical 51st state that doesn't exist yet, this is going to throw an error when we attempt to add this value into this table. Now we are going to be setting a primary key on the combination of state abbreviation and zip code. Now to make it clear, you cannot have multiple primary keys on a table because of the nature of clustered indexes, which we'll talk about later on. But you can have a composite primary key. And this effectively means that any foreign keys in this table must reference both of these columns and renders both of them required on this table. So let's try adding our very first city. So we're going to insert into cities, Las Vegas. And boom, we have successfully inserted this. And let's make sure our constraints work. I'm going to try to add Boston in here without a state. And boom, as you can see, this violates the foreign key constraint city state abbreviation foreign key. And now I am going to try to add Boston in without a zip code. And once again, violates check constraint city zip code check. So our constraints appear to be working adequately. So Las Vegas has many zip codes, right? Let's say that we've decided we want to store a different one for Las Vegas than the one we're currently storing. For this, we need to perform an update, and an update looks like this. Update cities, we are setting the zip code equal to this new one, and we are searching through the database where name is equal to Las Vegas. And as you can see, it says that it has updated one field. So now let's do an exercise. We've performed all 4 CRUD operations, creating, reading, updating, and deleting. So on your own, perform each of these actions with your own city, a city of your choice. Add it to the database, retrieve it, change its zip code, and then delete it. So pause the video here, and we will come back in a little bit to move on to the next section. Welcome back. Hope that exercise wasn't too much of a wrestling match. Let's move on to perhaps one of the most important qualities of a relational database, joins. So the join is a very powerful operation. It's basically like all of the databases we're going to talk about in this series can do CRUD operations. Joins are the aspect of relational databases that essentially empower us to do any query and retrieve any kind of data that we want, no matter how it is organized. That doesn't mean we can freely leave our data disorganized. We don't want our joins to be any more complicated than they have to be, but they can be pretty powerful tools and allow us to join a lot of seemingly disparate data together into an easily comprehensible format. So in preparation for illustrating these joins, let's just add a few more cities into our cities table. So let's start by performing what's called an inner join. So all joins return tables that in some fashion combine the values of the tables specified in the select statement. So for example, in this select statement, we specify that we want the everything in cities, so all of the columns in the cities table, combined with the state name from the states table. We're going to connect them with the on statement, and we are basically saying, give me all of the rows where the state abbreviations match between these tables and show me all of the city info plus the name of the state the city is in. And just to illustrate, I think the best way to visualize what a join is with a Venn diagram. So on the right side here, we have all of our states, and on the left side, we have all of our cities, and in the middle, we have all of the overlap between these two tables. So when we perform this join, we should get a table that contains all of the desired information about these 5 cities. And voila, here is that table. So we have the name of the city, the zip code, the state abbreviation, and the state name. And note, neither one of these two tables had all of this information. But because we are performing a join, we get a new table returned to us that has all of the overlapping information between these two tables. Now, there are other kinds of joins we can do as well. There are what are called outer joins. And in this case, we're looking at left outer joins and right outer joins, which in terms of our query, you can actually type in here, left outer join, or you can just say left join, and that is functionally the same thing. So a left outer join will return all of the contents of our first table and the overlap. And due to the way we set up our constraints, this result will be identical to the inner join with these tables, simply because we don't have any cities that do not belong to any states. So if I perform this query right here, you're going to see the results are identical to the previous one. Now on the other hand, when we perform a right outer join, we are going to get all of these states, regardless of whether or not they have any cities inside of them, as well as all of the overlap. So you can see we get the state name of Florida and Colorado, even though we do not have any cities in those columns. So just to illustrate, in this Venn diagram, this is our left outer join. We get all of the contents of this section of the Venn diagram. And in the right outer join, we get all of this section right here. Now, if we want to do a full outer join, this is going to return the entire Venn diagram. It is going to give us absolutely everything, regardless of whether it has any contents overlapping between them at all. So if hypothetically we had some cities that did not have states, we would get all of those cities listed, all of the states listed, and also all of the overlap. So if I perform this, this is essentially going to be identical to our right outer join, but just to illustrate, it is returning us absolutely everything. Now let's say, for example, we want to get the values where these tables do not overlap. Well, in order to do that, we simply need to filter out some of our information. And with that, we do what is called a where clause. So for example, let's say we wanted to get this stuff right here. We wanted to get only this left outer section of the Venn diagram. To do that, we would just basically do a left outer join, but we would filter out all of the contents that are inside of this center section right here. So where states.state abbreviation is null, does that for us. And you can see we get exactly what we would expect, a blank table. Now if we wanted to do a right outer join and retrieve only those values that aren't overlapping and aren't on the left side, then we do a right outer join and exclude all of the values that are in here. And as you can see, we are getting Florida and Colorado because we have excluded, or rather we are looking for values where cities.state abbreviation is null. Then lastly, if we want to get only these outer sections of the Venn diagram right here, we don't want to have any of the overlap. We perform a full outer join, and we look for where cities.state abbreviation is null or where states.state abbreviation is null. And voila, we are getting both of these sections, and it just so happens that this one is empty, so it is identical to our previous query. Let's go ahead and zero in on where our events are going to take place by adding a venues table. Now, when we're doing this, I want to focus on a few particular things. First being our venue ID. Our venue ID is going to be a serial primary key, and what this means is that every single time we add a new venue, the very first column, the column we're using as our primary key, is just going to be an incrementing integer, 1, 2, 3, 4, etc. And this is not only a very common way to set primary keys, but it's a best practice for reasons that we're going to talk about in indexes. But essentially, you want, in general, for your primary key to not be something that you're going to be inserting stuff into the middle of very much. You want it to be always additive, always increasing, and unless it's not something that's going to change very much. So for example, for our states, it's pretty unlikely that it's going to be changing very often other than the core 50 states. Therefore, it's probably relatively safe to be using the abbreviation as the primary key. But even then, one could argue that it would be better to have it as an incrementing integer, but since we're going to be searching on it so often, it kind of made sense for it to be based on the abbreviation. Anyway, these are the sorts of judgment calls you need to make, but in this case, since we are frequently going to be adding additional venues, it makes sense for our primary key to be an incrementing integer. For our foreign key, we are establishing a link between this table and our cities table via its two primary keys, the state abbreviation and the zip code. So remember how we set these up as the primary key on our cities table? So when we set a foreign key relationship, when we say, hey, when we reference that table, we are going to be going through the state abbreviation and zip code. This is the reason we are making this connection. Match full requires that either both keys be present or both keys be null. So that way you can't have one present and one absent, because on the table that we are referencing, we're going to want to have both of those as well. So let's go ahead and create this table in our database. So now let's add some venues into our table. So we are going to add my favorite karaoke bar that is unfortunately no longer with us, as well as a fictitious, I presume, location called Banana Land in California. And just to make sure we were successful, let's take a look at all of our venues inside of our table. So here we have Courtside and we have Banana Land, and if we were to expand this sideways, I'm not going to because it will mess up my camera settings, but essentially we have these items inside of our table and we are good to go. Now notice on this table that the venue ID has automatically been populated, just as we indicated that it ought to be with the incrementing integers. And let's also go ahead and illustrate our match full constraint. So in this case, we have attempted to add an invalid value because this is lacking a state abbreviation. Thus, when we look inside of here, it's saying venues, state abbreviation, zip code, forward key. The match full is not being satisfied, therefore it is erroring out as we would want it to do. So next, I have a challenge for you. This is a challenge that is going to require all of the skills that we have exercised so far. And don't worry, this is going to be a little bit challenging, so feel free to take your time with this and pause this video, but I will be going over a solution to this after you have given your attempt. So we're going to create an events table that has the following columns: an event ID, a name, a start date time, an end date time, and a venue ID. The event ID should auto-increment, and the venue ID should be a foreign key linking to the venues table. Name, starts, and ends should all be required basic text fields. And here is a hint. The serial primary keys produce an integer type. You are probably going to need to know that at a certain point in this challenge. Then you are going to populate your new events table with 3 events. One should have no venue. So for example, you could do a holiday for an event with no venue. And dates should be formatted in the way that I just described right here. After you have added your events, write a query that retrieves all information about an event at a given venue based on the venue's name. The returns table should also include the venue's address. So feel free to take your time with this. I am deliberately creating something that you're going to have to wrestle with a little bit, because that is the best way to achieve retention on these skills. So pause the video here and we'll come back with a solution. All right, welcome back. Let's go over my solution to this problem. So first, let's go over creating the table. We're creating a table called events. Event ID is going to be a serial primary key. This is going to be the auto-incrementing ID for the primary key first column. Name, starts, and ends are all going to be texts with the not null constraint on them that enforces requiring these fields. The venue ID we are going to be setting up as a foreign key into our venues table, which is this line right here. And it is going to be referencing venues, venue ID. So this makes sure these lines combined create the column and make certain that any foreign key that we are setting up here actually exists on the desired table. So moving into the inserts, we're going to be adding a few events right here. We're going to have a karaoke night that is happening at our first venue, which is courtside. We're going to have another event called Banana Shake that is happening at our second venue, which was the banana place in California. Now, we could not, in the same insert statement, have an event with a venue ID and an event that lacks a venue ID, because this would throw an error. So we needed to make a second insert statement that had name, starts, and ends for Halloween. And fortunately, since when we set up our table, we were not requiring that the venue ID exist, only that if we do put it in, it exists on the venues table, we are able to make such inserts. So if you put a not null constraint on your venue ID, this part probably gave you some trouble, because you need to be careful. Sometimes you don't necessarily want to have every single constraint on every single column. Then lastly, we have our select events and venue address, forming an inner join between the two venue IDs, and we want to find specifically all of the events that are happening at courtside. Thus, that should return a table. So let's see how it goes. We are going to do this. We successfully create our table for events. We perform our very first insert statement to get all of our actual venued events. And then we do another insert statement to add in Halloween. And then lastly, we are going to find all of the events that are happening at courtside. And voila, we have our karaoke night. So before we finish this section, I want to introduce you to this notion called an entity relationship diagram. You are probably going to run across these as you continue to work in relational databases, and you are likely to have to draw them as well. And all this diagram is doing is it is showing the relationships between the tables that you have inside of your database. And what this connector here means, that this is a one-to-many relationship. That is what this little branching symbol right here means. So states have many cities, and cities have many venues, and venues have many events. And then inside of each of these entities, we have all of the columns that are inside of that entity. So I thought this would be useful to you because you're probably going to run across these, and I would encourage you when you are trying to come up with the schema for your databases in the future, drawing out an entity relationship diagram like this can be very helpful in making sure you understand the structure of the database you're building and keeping it as simple as you can. So I'm a bit of a nerd when it comes to trying to find efficient solutions to things, trying to come up with really elegant designs for systems, and thus this section in particular of this presentation is perhaps my favorite because it deals very heavily with this and it involves some of probably the most interesting and elegant solutions in relational databases. And that topic is indexing. So indexing is just what it sounds like. It is a referencing method to speed up your database's ability to find desired information. So to understand it, we're going to need to know a little bit about how Postgres stores data on disk. And to help you with that, here's a few vocabulary words that it would behoove you to familiarize yourself with. So a page is a usually 8 kilobyte segment of information that is stored on the disk. And a heap file is it involves lists of unordered records of variable size. And it is important to note this is not the same thing as a heap data structure. These are unordered records that are going to be inside of a page. A database cluster is basically just where your database's data is being managed on the disk. And a tuple, for our purposes, is synonymous to a row inside of our tables. So here's how it works. Each table in your Postgres database is stored in a separate file. So every single time you have a new table, isolate this. This is one file right here. This file contains an array of pages, these 8 kilobyte pages. So you've got one file. This file is full of an array of pages. All pages are logically equivalent. So any given row on your table can be stored on any page. You can have row 1 on your table stored on page 1 and row 2 stored on page 5. Okay, these don't necessarily have to be in sequential order as they appear on the table. Pages are organized into heap files, and these files contain a collection of items or rows or tuples. At the front of these pages, you have pointers, and these pointers point to the ends of the page where the actual rows are stored. All rows on the database will be of the same byte length, which allows you to be confident in their location on the disk, because you know, okay, my rows are starting here. I know that if I am looking for the 5th row, that I just need to go the length of the row times 5, and I will have the index, the location of the data that I am looking for. In addition to the pointers at the front of the page, there are a whole bunch of headers, but we're not going over them because they are not important for understanding indexing. So here is an illustration of what I just described. We have our table file. Our table file consists of these pages right here. And if we zoom in on a page, we'll have a whole bunch of headers. And then here, we're going to have these pointers that are pointing to our rows that are all at the end of the page. And in between these things, we're just going to have a bunch of null data that is just filler that can be expanded into as we need to. Okay? So now, let's say we have created a table and we have a primary key on this table. When you create a primary key, you are creating what is called a clustered index. And a clustered index is different from all of the other indexes we're going to talk about because it essentially sorting the data on the disk itself according to the column by which we are indexing. So for example, we had our states table and we sorted, our primary key on the states table is the abbreviation for that state. Therefore, if you were to look at the data in our states table, you would see that all of our data is sorted alphabetically according to the abbreviation of that state. Now, if we had an auto-incrementing primary key, then all of the data in our table would be sorted according to the value of that primary key. It would be 1, 2, 3, 4, and so on. Okay? So this is why you can only have one clustered index, because there is only one index by which you can only sort all of the data by one item. You can't sort by like you could organize it, you could like have a hierarchy of organization, but at the end of the day, you can only actually sort the data by one other thing. If you want to index in any other mechanism, you need to do it in some other fashion. Thus, when you are doing lookups by the clustered index, by the primary key, that is the single fastest way to retrieve data, because you are literally just iterating through the stuff as it actually appears on the disk. You don't actually have to look in multiple different locations on the disk in order to find lookup values and find pointers and so on. You are iterating through the values as they appear on the disk. There is nothing faster. Likewise, this is why it is really important when you have a clustered index that it needs to be something that is static or something that is only ever going to be incrementing. Because let's say we were to add a new state to the United States, and let's say it just begins with M, so we're going to be inserting it into the database somewhere in the middle, right? We can't simply do that because everything is in order, right next to each other. So, in order to add this new item, we would need to take all of our data and move it to a completely new place on the disk and move it in such a way so that you insert the new stuff and then copy it all over. If you have a really large database, that is going to be a massive undertaking for your computer. So, you need to be very careful about what you choose to be your primary key and how you structure your clustered indexes. Because if you are careless about it, it's going to make your insert and delete operations unbelievably costly in a way that won't necessarily be obvious if you don't understand how this mechanism is working. So, how do other indexes work? So, think of it like this. When you create an index, you are creating a list of key value pairs where the keys are the values of the items you're looking to index, and the values are the locations of those items. So let's take a look at this. Let's say we have a database that some of which involves fruits, right? But the fruits aren't necessarily like the database isn't ordered alphabetically by the name of the fruit. Maybe we have a bunch of different groceries, okay? So we want to have an index that can tell us where the location of apples is, where the location of bananas is. So this index, this list, is sorted by keys, and the keys are equal to the values that we want to have. So if I say, I want to know where apples are, then this says, okay, apples are on page 2 at index 5. I want to know where grapes are. Grapes are at page 1, index 10. Okay? So that is the way an index is structured when it is not a clustered index. So we have this index, and these locations constitute a page and index of the desired item. These key values are sorted by their keys, and by default, if you just create a generic index in Postgres, it is going to be what is called a B tree. And a B tree you can think of as if you're familiar with a binary tree, it's a tree where everything to the left of a given node is going to be less than that node, and everything to the right of that node is going to be greater than that node. And you can traverse this tree to find the item you're wanting, and it's very efficient. It is going to have an efficiency of log base 2n, where n is the number of nodes in the database. So the more stuff you have, the more efficient it gets. It's a very desirable approach to indexing. It's going to be way, way faster than if you were to simply iterate through every single value in your database. So, binary tree, very efficient, but it's not the only way that you can do it. There's a whole bunch of other data structures that are used in Postgres. Another popular one is hash tables. There's far too many for me to get into in an introductory course like this, but suffice to say, there's more data structures available than just B trees. So, why wouldn't you just index everything? If adding an index is going to make things faster, why wouldn't you do it all the time? Well, when you are adding an index, you are making a trade-off between improving the speed of your reads and space. Because every time you add an index, remember, you need to create another one of these lists that contain redundant information, right? You are repeating all of the values that are inside of your database, again, inside of this list in order to create a bunch of pointers. That takes up more space. And the more indexes you add, the more space it's going to take up. Now you might think, well, disk space is cheap. Why would I care about that? Well, this isn't only disk space. This is going to be RAM as well. So when you have a system that's operating and you're getting a lot of hits, your memory is going to be consumed by all of these indexes, and that can actually cause performance problems if your database is getting really big. Another thing you need to take into account is spatial locality. And this is literally the locations of the items and the indexes on your disk. And this is a fairly deep topic that I don't want to get into too deeply right now, but suffice to say, if you are not aware of how you are retrieving all of this information on your disk, if your index is not efficiently spatially local, like the items in your index are not actually located next to one another on the disk, you can wind up in a situation where your index actually slows down your read because of how often your computer needs to bop between different locations on your disk, as opposed to if it just needed to literally read through the rows that were all next to each other inside of the same file. Just to illustrate this a little bit, this is a slide from a presentation from my mentor talking about various search algorithms. And you can see, if we have a linked list, usually a linked list can be very efficient in terms of how it goes about its search. However, if there's poor spatial locality between different items on the linked list, and your computer needs to be looking all over the place for the different values, you can actually have it be very inefficient. In fact, the least efficient of all of the options available listed here. So you need to be aware of that. And lastly, generally speaking, when you're doing indexes, you need to be aware of your use case. Are you likely to be doing more reads than writes? Now, you're going to be getting an exponential improvement in your read speed, right? You are going from OX to O log X in your read functionality. That is a massive improvement. But you also need to be aware that when it comes to writes and deletes, you're going from constant time to O log X as well. So that's not so great. If you are doing some sort of logging database where you're going to be writing all the time, you probably don't want to have any indexes whatsoever. You want to just be appending to the end of the database more and more and more, and on the one rare occasion when you need to do a read, you will just take the extra time that takes. Fine. So be aware, am I mostly going to be reading from this database? Am I mostly going to be writing? If it's the latter, you probably don't want to be doing indexes. So this all having been said, let's create some indexes on our events table. So this first one we're going to do is a hash index. Now, a hash index is only capable of equality evaluations on a single field. It is literally a hash data structure. You're looking at a key, you're looking at the value, and so on. Now, this is nice because it takes up less space and it has constant time lookup operations, which a B tree would involve O log n as opposed to constant time. It is thus superior for our use case. However, in situations if we needed to iterate through the indexes more frequently, if we wanted to do evaluations on more than a single field, the B tree would probably be the superior choice. So in this case, we happen to have a use case where a hash index is superior. So we're going to create a hash index, and this is the query we run in order to do that. Voila, create index successful. Now, it's probably going to be a frequent case that we're going to want to look at the start dates and times of the various events in our database, so we probably want to be creating an index for that. So let's go ahead and create a B tree index for events underscore starts. And voila, we now have that index. So now we are able to look up events by name or date, and we won't need to iterate through the entire list every time we want to do that. We will be able to use our index, and it will be substantially faster than the alternative. Let's say you're in a situation where you need to collect a whole bunch of information from a number of different rows, and you want to illustrate this information in a easy to digest for a human way that just prints everything out inside of a simple table. To do this, oftentimes we use what are called aggregate functions. So the simplest of the aggregate functions is the count function, and it is simply you are looking through a large number of rows and you are counting the number of rows that are there. So for example, if we want to count how many rows we have inside of our events table, we can do that and it will return to us 3 rows. When we perform a count function, the value in the parentheses is the columns on which we want to count. So with star, we are including all columns, but we can be more specific if we want. So for example, if we only want to be counting the name column in the events table, and we want to find all occurrences where the name of the event is similar to Halloween, we can run a query like this one. Just to clarify, the like operator looks for an approximate match. Obviously, if we wanted to find exactly Halloween, we could use an equal sign here. But in this case, we're doing like Halloween, and we have a wildcard value right here, which means it's going to start with Halloween and then have any value after this. So this will find Halloween day, Halloween night, Halloween party, anything like that. So if we want to run this query right here, it finds the one occurrence of Halloween that I have added to my events table. Just for your personal reference, if we want to do an underscore, this will match any single character. And if we want to do a like operation, but ignoring case, we use iLike. So let's add some more data to our database in preparation for the next query we're going to be doing. And now, let's say we want to find out how long has Courtside been doing karaoke. Let's retrieve from the database the earliest start time and the latest end time for all events that occur at Courtside. So we are going to select the min starts and the max ends, so the earliest start date and the latest end date, from a table that is formed when we perform an inner join between venues and events where the venue name is equal to Courtside. So when we perform this query, we find that the earliest start date in this table is August 15th, 2020, and the latest end date occurs on August 17th, 2020 at 2200 hours. So now let's say we wanted to count the events at each venue. We wanted to know how many events occurred at every single venue, and we want to have a table where we have the venue's name or the venue's ID and the number of events that happened there. Now you might imagine if you wanted to do this, you would need to write a whole ton of select statements, right? Select, count, blah, from events where venue ID equals 1, 2, 3, and you would need to do this a whole lot, right? Massive pain. Fortunately, this is pretty common, and Postgres has a solution to it. It is the group by function. If you're familiar with pivot tables in Microsoft Excel or something like that, this is essentially doing the exact same thing. You are grouping into an easier to digest table of sorts the information that you are looking to get, the venue and so on. So it's a little bit easier to understand if we do it. So we are selecting venue ID and count. So we're creating a table that's going to have the venue ID in one part and the count in the second column. We're going to select that from events, and we are going to group by venue ID. So every single time you get the same venue ID, you are going to add it into the same row that you are displaying for that particular venue. So let's just illustrate exactly what this looks like. So as you can see, we have 3 occurrences of venue ID 1. But instead of saying venue ID 1111111 3 times, it takes those occurrences, groups them up here into this same venue ID row, and increments the count on this column right here. So what if we wanted to find all the values that exist, aka are not null, and have more than one event? So we want to find the most popular venues in our database, everything that has 2 or more events that have happened there. In this case, we can't use a where, because you might imagine yourself saying, well, I want to find all venues where the number of events that have happened there is greater than or equal to 2, right? But we can't do that because we're doing group by, and group by doesn't allow for a where clause. Thus, we have to use the alternative, which is called having. Having is built to do the same thing that where does, more or less, but in the context of a group by. So, similar idea right here, select venue ID and counts from events, group by venue ID, and now we're going to say having this count value greater than or equal to 2, and venue ID is not null. So we don't want to have any venues that, we don't want anything in our table where hypothetically you could have an event that doesn't, right, we have Halloween, right? We don't want to have any cases of events with no venues. We only want to include venues with more than one event. So when we perform this, we should get only courtside, and it's going to tell us, hey, look, you have had 3 events here. As a best practice, just to note, when you are performing these group by functions, you generally want to be grouping by primary keys. And this is because of the way the indexes are set up. You don't want to be bopping all over the place on your disk in order to perform all of these functions, in order to be executing all of these statements that you need to execute. You want to be keeping the number of places that your software needs to move across a disk to a minimum. And by using your clustered indexes for that purpose, it is going to run much, much faster than if you do it on something that is not indexed or something that is working on some other kind of index. As a final note, let's say you want to get all unique values from a column, right? You can do that fairly simply by simply running select venue ID from events, group by venue ID, right? That will get you only the unique IDs. But hey, this is such a common query to be run that Postgres has built into it its own little tool. It's called distinct. So all you need to do is say select distinct venue ID from events, and it will basically perform this exact thing for you, but in a slightly more elegant manner. So to summarize, the simplest aggregate function is the count function. To aggregate a list of data about a variety of rows, use group by. To filter through the items you've group by'd, use having as opposed to where. And if you want to find all unique entries in a table, use select distinct. All right, let's talk about the last section of this presentation, transactions, perhaps one of the most appealing aspects of Postgres and other relational databases. So let's say you're in a situation where you're doing finance or some other similarly high-risk activity where you really care about making sure that every time you write something to the disk, that it is absolutely being written to the disk there. And anytime you get information from the disk, it is absolutely accurate, right? You're in a situation where you don't want, you deposit money from one account and withdraw it from another. You don't want any interaction happening between those things because that's going to have legal consequences for you. That's going to make some really unhappy customers. For that situation, relational databases offer transactions, and they are probably the main reason a lot of people go to these sorts of databases. They guarantee that every command in your query is executed, and if anything fails, the entire procedure is rolled back. PostgreSQL transactions are ACID compliant, and thus for every command we've run, a transaction has been wrapped around it. This has been happening behind the scenes, but built into the database, every single one of these queries that we have run for this entire presentation, and indeed, every query you will ever run in Postgres unless you deliberately try to turn them off or you're deliberately avoiding them, is going to be wrapped in a transaction. So, we have been using them this whole time without even knowing it. So you can explicitly begin a transaction with the begin transaction function. You can terminate it with rollback, and otherwise you can end it and persist it with end. So let's do a little demonstration right here. If I begin this transaction, I'm going to delete from events. I deleted absolutely all of my events. Everything is gone. Oh no. Well, I'm going to roll back and it's going to be perfectly fine. The transaction has been completely rolled back, and if I were to do a select star from events right now, I see that I still have all of my events. That delete has not been persisted to my database because I did not end my transaction. So transactions are most commonly used when you're modifying multiple tables and you want to make sure that all of those changes keep in sync. And like I mentioned, the standard example is when you have an account and you want to grab some money from one account, move it into the other account, and so on. You're in separate tables, but you want to make sure that everything happens in the order you want it to happen and exactly the way you want it to occur without anything messing it up. In that case, you begin a transaction, you update it, and then you end it. So one of the nice things about transactions is that when you are modifying something in your database, the thing you are modifying is locked. Nobody else can modify the thing that you are working on. And I am going to demonstrate that for you right now. So let's say I am going to begin transaction. And I am going to update one of our events so that it is now occurring at courtside as opposed to wherever it was occurring before. So I am now updating it. Now I am going to go to another window and I am going to try to update another event. When I do this, you can see it successfully did it, and this has been already wrapped in a transaction. It processed the entire thing. But now let's see what happens when we try to update the same event that this window is currently updating. So I go here. Look at that. It's hung up. It is not editing this value that we are trying to edit. And in fact, it will not edit it until I go to this other one and I end the transaction. I end this transaction, it commits it, this updates it, and then this value gets updated immediately here because it is no longer locked and immediately updates. So that is one of the powers of transactions. They make sure that as long as you are committing your transaction, as long as you are in the middle of it, nobody else will be able to touch the data that you are modifying. Alright, well that's everything I have to say about Postgres for this video. I will probably be making a sequel video to this where I will delve into certain topics a bit more deeply and add some additional functions that will be useful to you. But I want to get to the other database types first, so this can be a sort of complete series. Here is my bibliography. I leaned heavily on 7 databases in 7 weeks for the creation of this video, so I highly recommend checking that out, as well as the Postgres docs, which can always be useful. If you have any recommendations, this was a fairly new format for me where I was doing the demonstrations of the implementations of the code in this video at the same time I was presenting it, so if you have any new suggestions for formats or if this worked well, please feel free to let me know in an email or in a comment. And again, if you need to reach out to me, you can do so at howard.reith@gmail.com. Thank you very much for watching. Have a good one.